Hi, I'm Mr. True. In this video, we are going to learn the basic idea of a matrix. And then we're going to use this matrix notation to solve a system of equations using the Gaussian elimination method. And then we're going to be able to, with this new notation of matrices, learn new ways to solve these relatively, or actually sometimes very complicated systems of equations in a much more efficient manner than the Gaussian elimination method. All a matrix is sort of a way of allowing you, how we're going to basically be using it, is a way of sort of writing systems of equations in shorthand notation and not have to include all the variables. So let's get the very, very basics down here first though. A matrix is a rectangular array of numbers set inside some square brackets. That's it. Each number in a matrix is called a matrix element. So I'm giving you an example of a 3 by 2 matrix. This means this is a 3-row and 2-column matrix, as I've identified here. And the elements in our matrix A, we need to name those, are, if you go by row, 4, 2, 3, 0, and 0, 5. Now, I've put an oval around the first column and the second row. Where those ovals are intersecting are around this element of 3. So element 3 is in row 2. Let's see, row 1, row 2, row 3. Okay, it is in row 2. And column 1. So my textbook that I'm teaching out of uses this notation. We can say that element 3 is in row 2, column 1, or we can just identify it with symbols. We have matrix A and then 21. It looks like 21, but what it's saying is that 3 is in matrix A and it's in row 2 and column 1. Now let's get this board erased and see how we can write equations, actually specifically systems of equations, as a matrix. Bang! Okay, so we want to represent a system of equations with a matrix. Our first example is x minus 2y equals 5 and 3x plus y is equal to negative 4. That written in matrix format is 1, negative 2, and 5, 3, 1, and negative 4. And as you can see here, in my systems of equations, I've kept my x variables lined up in columns. That's very, very important. And then we have the x coefficients of 1 and 3, and that's the first column of my matrix. Then I have negative 2 and 1. Okay, those are my coefficients for my y's, and it's my second column. And then I have this vertical line representing the equal signs. That means that this is an augmented matrix. I'm basically putting together a matrix of the coefficients of all my variables and a matrix of just the constants at the end. We have 5 and negative 4. So we have the x coefficients, the y coefficients, the equal sign represented as a vertical line, and then my constants of 5 and negative 4. Now down here I have 3 equations and 3 unknowns, but you can see my unknowns here I have x, y, and z, but some of my equations are missing some of those variables. So let's see what that looks like as a matrix. Well, I'm going to start off and I'm going to do my x coefficients in my first column. So if there is no x in that particular equation, we're going to have to put in a 0. So the first equation has, of course, an x variable. Its coefficient is 2. My second equation has a x coefficient of 3. And then finally my third equation has a coefficient of x, which does not, there is no x, so its coefficient is 0. Then we're going to do the y's. We have no y in the first equation, so its coefficient is 0. We have a coefficient here of negative 1, and then finally of 2. Then for the z's coefficients, we have 1, 4, and negative 2. Then our augmented line and our constants, well, we have our constants of 4, 1, and negative 3. So now that we know how to take our systems of equations and represent it as an augmented matrix, let's get the steps down that we need to actually go through, given a systems of equations, let's get it written as a matrix and solve for those 3 variables or 2 variables, whatever is in your systems, using the Gaussian elimination method. Series of our steps we're going to walk through to do the Gaussian elimination. We're going to write our system of equations as an augmented matrix. We're going to use row operations so that when we add the rows, we get a coefficient of 0. we're going to multiply one or two of the rows by some number or numbers so that I can, when I add those rows together, I get a coefficient or a value of 0. And we're going to keep that process going until we get an identity matrix. In other words, the left side of our augmented matrix is going to have a diagonal row of 1s, and every other element is going to be 0. Then when we look to the right-hand side of the matrix, the constants, we're going to have our answers for, you know, x and y, x, y, z, a, b, c, whatever letters are in your system of equations. So we have 3x minus y equals 3 and x plus 2y equals 8. We're going to write that as an augmented matrix here. And that becomes, well, just write it without the variables. So we have 3, negative 1, and a constant of 3. And then we have 1, 2, and a constant of 8. So what we want to do first is, remember, I want this diagonal row to be 1s and everything else be 0s. So I have a value of 2 here, and I have a value of negative 1 here. So what I want to do is we're going to come out here temporarily and write a matrix which is going to be equal to, let's see, what do I want to do? I want to take the first row and multiply it by 2. So we're going to do 2 times row 1. And that is going to be 3 times 2 is going to be equal to 6. Negative 1 times 2 is going to be equal to negative 2, our augmented line. And then we have 2 times 3, which is equal to 6. And then I want to keep row 2 the same. So we're just going to write 1, 2, and 8. Now what I want to do is I want to add these rows up, and I want to replace the first row and get that value of 0 there. So I want to do row 2 times row 1 plus row 2. So 2 times row 1 plus row 2. So I've already taken 2 and multiplied the first row to it. I want to multiply that with row 2 and replace it in where I have this mark here of row 1. So 6 plus 1 is equal to 7. We have negative 2 plus 2, which is equal to 0. And we have 6 plus 8, which is equal to 14. And we're going to keep the second row the same, which again is 1, 2, and 8. So let me get this scratch work off to the side here. Now what I want to do is I want to get this element equal to 0. Or, yeah, let's go ahead and do that. Because the order that you do these is kind of up to you. At this point I could, and maybe I should, let's go ahead and take this first row and divide it by 7. So we're going to make another matrix here, and I want to take the first row and divide it by 7, or multiply it by 7. So I'm going to do 1/7 of row 1, and that is going to give me 7 times 1/7 is equal to 1, 0 times 1/7 is equal to 0, and 14 times 1/7 is equal to 2. And then my bottom row again is 1, 2, and 8. Okay, I would like to make this equal to 0. So I want to do some kind of addition with these rows, and I want to do a substitution into the second row. So I want to take, let's see here, if I take this first row and multiply it by negative 1. So I want to do negative 1 times row 1 plus row 2. So I want to, see I have no notation here on the first row, so I want to keep that the same. So I want to have 1, 0, and 2 here. Now I want to take the first row and multiply it by negative 1, and instead of writing the scratch work off to the side, I'm going to take my different colored chalk here and take negative 1. I want to go back to this row here, negative 1 times row 1, and multiply it, well, by what I've indicated, negative 1. So 1 times negative 1 is negative 1, 0 times negative 1 is 0, and 2 times negative 1 is equal to negative 2. And that's actually how I do my own work, is I keep the scratch work above here. I mark off what I want to do in my new matrix, but then I do the scratch work in the matrix above it. So negative 1, I want to take negative 1 times row 1 plus row 2 and keep it in row 2. So negative 1 plus 1 is equal to 0. 0 plus 2 is equal to 2. And negative 2 plus 8 is equal to 6. So now again, this new row came from -1 times row 1 in the previous matrix plus row 2. Now, I don't have the identity matrix yet because this is still equal to 2 and not equal to 1. So we're going to come up here. I got 1, 0, 2, and I want my new row 2 to be equal to or come from taking this row 2 and multiplying it by half or dividing everything by 2. So I want to do 1/2 times row 2, and again I want to do that from the previous matrix. So 1/2 times 0 is 0, 1/2 times 2 is 1, and 1/2 times 6 is equal to 3. And so now this row here becomes 0, 1, and there's my diagonal of 1, so this is going to be the identity matrix. Everything else is 0 with a diagonal of 1, going from the upper left-hand corner to the bottom right. And then, of course, half of 6 is equal to 3, and I'm done. So remembering that my first column is where my x terms were at, I have x is equal to 2. The second column were for my y coefficient, so y is equal to 3, and this is the solution to this systems of equations. Again, doing the Gaussian elimination method, only writing it out as matrices as opposed to continuously writing over and over and over again the x's and y's. If I want to make sure that that works, of course, I can check my answer by taking those values, plugging them into here. So I have 3 times 2 minus 3. Let's make sure that that's actually equal to 3. We have 3 times 2 is 6, and 6 minus 3 does equal 3. So my solutions work for my first equation. My second equation, x plus 2y equals 8. Well, let's see, x plus 2y equals 8. 2 times 3 is equal to 6. 6 plus 2 is equal to 8. So I've got my first answer right. Let's go on to another example. This next example isn't going to take very long. You might even see the solution before you even start the problem. Solve the system of equations 2x minus y equals 10 and negative 2x plus y equals 1. Well, that written in matrix format is, well, just write it out except for no x's and y's. Here's the equal sign. And I want to make a new matrix. Where'd my chalk go? Here it is. Well, let's see. I've already got a set of opposite coefficients, and actually I have both pairs that are already opposites. And so we're going to try and take the first row here. Let's see. We want the new row to be a result of row 1 plus row 2. So we have 2 plus negative 2 is equal to 0. 1 plus negative 1 is equal to 0. And then we have 10 plus 1, which is equal to 11. And then our bottom row stays the same. We have negative 2, 1, and 1. Now, something's a little bit weird here, right? Because I'm supposed to make a diagonal of 1s, and every other element in my matrix I want to equal 0. But if you just stop for a second and look what I've written here in the first row, I'm saying that 0x, plus 0y is equal to 11. Anything times 0 is 0, so we're saying that 0 plus 0 is equal to 11. Well, that's not possible. So this is no solution. So you do need to keep your eyes open for the possibility, as we run through these matrix problems, as you do them yourself, that we can have a possibility where there's either an infinite number of solutions or no solutions, as this one has. Next example is going to have a 3 equation and 3 unknowns. Bam! For our third example, we have 2x plus y minus 2z equals negative 1, 4x minus 2y minus z equals 5, and x minus 2y plus 3z is equal to 6, and I've written it in our augmented matrix form. Now we are, again, the matrix format is sort of shorthand for writing the system out without having to write all the x's and y's, and in this case z's, but the Gaussian elimination method is still going to be long and tedious, so be meticulous with your work. Write some notations as you go to let yourself know what you did. In case there is a mistake, you can go back through your work and more easily find the mistake. And again, with these matrix notation, we are going to find quicker ways of solving these systems. But for now, we're doing the Gaussian elimination method. I'm going to tend to get the lower left-hand corner equal to all zeros first, and then start getting my diagonals to equal 1 and working my way back up until I get my identity matrix. And basically, once you get your bottom left-hand corner to all equal zeros, if you were not in matrix format, you would start your back substitution process to find, well, we'll have z, then you'll do your, be like the same as finding your back substitution to find your y's and your x values. Okay, I'm going to do a couple of things per step here so I don't run out of room. I want to keep row 1 the same. So we're going to do 2, 1, yes, 2, 1, -2, and -1. Now I want to do some kind of multiplication with the first and second row to get this value to equal 0. So I want to take, let's see, if I want to take the first and second row and add them together, I've got a 4 here already. If I multiply this 2 by -2, then I'll be able to add these rows and make this element equal to 0. This is what I'm focusing on right now. I want to make that 4 equal to a 0. So I want to do -2 times row 1 and add it with row 2. And I'm writing this in the second row because that's where I want to do my substitution. That's where I want to put my new row that I get from adding row 1 and row 2. Okay, I want to take -2 and multiply it by row 1. So I'm going to come up to the previous matrix and take -2 and multiply it through this row. So -2 times 2 is -2, -2 times 1 is -2, -2 times -2 is +4, and -2 times -1 is +2. And I want to now add that new row of numbers with row 2. So we have, oh, excuse me, it should be -4. Okay, I did all my other multiplications correctly. So -4 plus 4 is equal to 0. -2 plus -2 is equal to -4. 4 plus -1 is equal to 3. And 2 plus 5 is equal to 7. Okay, now what I want to do is I want to make this element equal to 0, and I'm still going to use the first row. Well, the first row, the element up here is equal to 2. I want that to be 0. So what would I have to add by 2, or add 2 to get 0? Well, this needs to be -2. If I can make this element -2, then when I add it to the first row, -2 plus 2 is going to be equal to 0. So for my third row here, I would like to take row 1 and add it with -2 times row 3. So, and I can look back later if I've made a mistake and see my notation here to see what I've done. Row 1, 2, 1, -2 and -1. Notice I'm looking at the original line now. Plus -2 times row 3. So -2 through here, 1 times -2 is -2. -2 times -2 is equal to 4. 3 times -2 is -6. And 6 times -2 is -12. Okay, so row 1 plus -2 times row 3. 2 plus -2 is 0. 1 plus 4 is equal to 5. And -2 plus -6 is -8. And 1 plus -12 is -13. Check my work. Okay. Now what I'd like to focus in on is making this element equal to 0. Now I can't use the first row anymore because its first element is 2, and if I combine it with row 3, of course, there's no way I can keep that equal to 0. So I'm stuck using the second and the third row. So we're going to come up here. Give me some brackets here. We're not going to touch row 1 or row 2 in this step, so I'm going to just copy those over. 2, 1, -2, and -1. We have 0, -4, 3, and 7. And now let's work on that third row. I want to be able to add these and get a sum of 0 in my third row. So I need those to be opposites. The lowest common multiple between 4 and 5 is 20. So I'm going to take, they're already opposite numbers, so I'm going to take row 2 and multiply it by 5. So I'm going to do 5 times row 2 2 and add that with 4 times row 3. And let's put the notation up here. Second row, 5. All right, 0 times 5 is 0. Negative 4 times 5 is negative 20. 3 times 5 is 15. And 7 times 5 is 35. I want to take 4 and multiply it to the third row. So 0 times 4, 5 times 4, negative 8 times 4, and negative 13 times 4 is negative 52. 4 times 10 is 40, and 4 times 3 is 12, so 52. And now I want to add those. So we have 0 and 0 is 0, negative 20 and 20 is 0, 15 minus 32. Well, 32 minus 15 is 17, and this is kind of like the largest number, so it's going to be negative 17. And negative 52 minus, or plus 35. Well, 52 minus 35. 52 minus 30 is 22, and 22 minus 5 is 17. The 52 is the bigger number, and it's negative, so it's negative 17. And let me just check here, make sure it's all right. Good. Now, at this point, if you were not working with matrices, you'd have something like negative 17 z equals negative 17. You would divide by negative 17, you get z equals 1, and you would start back substituting through your previous or your other equations until you find all 3 variables. We are going to find the identity matrix, so we're going to take this third row and divide it by negative 17. So we have 2, 1, negative 2, and negative 1. We have 0, negative 4, 3, and 7. And then we have 0, 0, 1, and 1. And again, that was from doing negative 1/17 times row 3. Now, I would like to make that 3 equal to a 0. Again, cannot work with the first row because if I add them, I'm going to get this first element to not be 0 anymore. So I need to work with the second and the third row. So we're going to keep the first row, 2, 1. Actually, can we do 2 steps here? Well, I got room. I'll do 1 step at a time. 2, 1, negative 2, negative 1. And for the second row, I would like to do row 2 plus. Now I want to make this 1 add up and make that 3 equal to 0. So I need this 1 to be a negative 3. So we're going to do row 2 times negative 3 times row 3. And keep the last row the same. So we're going to do negative 3 times row 3 is 1 times negative 3, 1 times negative 3, and now we're going to add those. So we have 0 and 0 make 0, negative 4 and 0 make negative 4, 3 and negative 3 make 0, and 7 minus 3 is equal to 4. We're now going to again get this to equal all values of 1. So we're going to simply take the second row and divide it by negative 4. So we have 2, 1, negative 2, and negative 1. We have 0, 1, 0. We're dividing by negative 4, so it's going to be negative 1. And then 0, 0, 1, 1. And again, just to keep the note, we took the second row and divided it by negative 4, or multiplied by negative 1/4. We're almost done. We now have to get these elements to equal 0. So this time I am going to do, let's see, how about we just work on making this element equal to 0. So if I can make that a 2, and add it with the negative 2, we get 0. So we're going to keep the second and third row the same. 0, 1, 0, negative 1, and 0, 0, 1, 1. We're going to do row 1 plus negative, nope, we don't need a negative, plus 2 times row 3. So going back here, row 3, multiply it by 2. And we get, except I wrote 3, why did I do that? So it's saying row 3. We're going to multiply that by 2. Yes, that is what I wrote. And 2 plus 0 is 2. 1 plus 0 is 1. Negative 2 plus 2 is equal to 0. And negative 1 plus 2 is equal to 1. Okay, we're almost done. I just have to make that one last element equal to 0. We'll just about be at the identity matrix. So we have 0, 0, 1, and 1. 0, 1, 0, negative 1. And then finally, let's see. If I take row 1 and I add it with negative 1 times row 2, because they're already the same number, I just need the signs to change. So I'm going to take row 2 and multiply it by negative 1. And add, we have 2 plus 0 is 2, 1 plus negative 1 is 0, 0 plus 0 is 0, and 1 plus 1 is equal to 2. Okay, well, last step, take the first row, divide it by 2, and we get 1, 0, 0, 1, 0, 1, 0, negative 1, and 0, 0, 1, 1. And let me just make sure that I have not made any mistakes. I feel like I have. Nope, I'm good. All right, so that is your first 3 by 3 matrix, or three variables and 3 unknowns. I'd like to do one more example, only I'm just going to let you figure it out and then give you the solution, and we'll call it a day with this video. Thank you very much. Here's our last example, the one that I'm going to allow you to do and then just give you the solutions to. We have 2x plus 2y plus 5z equals 20. Y minus 4z is equal to negative 16. And 3x minus 2y plus 9z is equal to 36. There is no x in the second equation, so don't forget to plug that 0 in when you set up your matrix. And we'll take a little bit of a pause and then come back with the solution. And hopefully it's the same one that you got, and you really do finally, or do completely understand how to do the Gaussian elimination method with some matrices. I'm Mr. Taru. Hi! Go do your homework.